Hi there. Thanks for coming by. We have a big lesson to do today. Big because it kind of represents the end of what we've been studying with vectors, and big because it's long. We're going to look at the intersection of three planes today, and the system of equations that would be represented by three planes. So, I don't know, maybe pour yourself a cup of hot chocolate or something to relax. Plan to maybe take this lesson, not all at once. Be ready to take a break, and I even recommend a good spot to do that too. So it's the only lesson we're going to do this week, but like I said, it is a big one. Come on, let's go. Let's get to it. Let's start with a simple algebraic question. Suppose we have three linear equations. Perhaps the first one is 2x plus y minus z equals 5. A linear equation with three unknowns. And suppose we have a second linear equation also with three unknowns, the same three unknowns. I'm just making up values here. And suppose there is a third one as well. Maybe 4x take away y minus z equals 0. So that's a linear system with three equations and three unknowns. And we might be interested to know what kind of solutions or what kind of x, y, and z values there are that satisfy all three equations. Maybe there's one value for x, y, and z that satisfies all three equations. Maybe there are no values for x, y, and z that satisfy all three equations. Or maybe there's an infinite number of values that satisfy all three equations. How can we tell? Well, one thing that we know is that each of these equations represents the equation of a plane. So if I were to take the first equation and look at all the values of x, y, and z that satisfy this equation, I would get the graph of a plane. So really, finding solutions to all three equations is actually the same as finding the intersection of three planes. And that's the geometry side of it. So if we want to know what kind of solutions we can expect to this system, which we do, then we might start by looking at the intersection of three planes and seeing what kind of possibilities there are. Now, as it turns out, looking for a common intersection of three planes in space, there are a lot of possibilities, and we're going to dive into those right now. Here are our first three possibilities. These are sort of the boring possibilities, I guess you might say. Now, as we work through these examples, we're going to assume that our normals are all n1, n2, and n3. And we're going to talk about what kind of intersection we might see and what kind of geometric properties are associated with each picture. It's hard to draw planes, but if you look at the first example, it's clear that all three of these planes are parallel and they don't intersect. So there is no intersection. In the second diagram, although it's not, you can't tell exactly what's happening, because one of the planes is shaded in, I think it's fair to say that two of the planes are the same, and one of the planes is parallel and not the same. Well, there still is no common intersection. Yes, two of the planes intersect, but not the third. They don't all intersect at any of the same places. And finally, in the third possibility, we have all three planes being exactly the same. That would correspond to all three equations being exactly the same, which is kind of a silly example, but we should still consider it as a possibility. In that case, our intersection is just the plane itself. Now, all three of these diagrams have some geometric properties that are the same. Notice that in all three cases, n1, n2, and n3 are collinear. So those are the normals. Remember that the normal to a plane is a vector that is perpendicular to that plane. And that normal completely describes the direction of the plane. And so in all these examples, those normals are collinear. Now in the first one, the equations or the planes are distinct. In the second one, two planes are coincident. They're exactly the same. And the third one is distinct. And sorry about my spelling there. And in the last one, all three planes are coincident. And then, of course, in all three examples, we have all three normals that are collinear. There's three possibilities there. Let's look at the other possibilities. Here are two possibilities, and you might notice what these two have in common. So in the first one, we have two planes that are coincident. So we have two coincident planes. And a third one that is not. That means that two of our normals are collinear. They're either exactly the same or they're parallel. One is like a scalar multiple of the other. And we do have intersection. The intersection is right here, and it's a line. And actually, that's the exact same kind of intersection we saw when we looked at the intersection of two planes, because really this is like having the intersection of two planes. If two of your planes are coincident, that would mean that really they're the same plane and the intersection is just that line. Let's look at the other example. Here we have what they're trying to show in the picture here is that we have two normals that are collinear. But the planes are not coincident. They're not the same. In that case, there is no intersection. Okay, yes, there are two lines here, and each of these planes does intersect the third plane in a line, but there's no common intersection. All three planes don't intersect in the same spot. And when we're talking about solutions to equations, we want solutions to all of the equations, not just two of the three equations or whatever it might be. So in this case, no intersection. So again, these two examples have this in common, that both have two normals that are collinear. So what about the example where none of the normals are collinear? Well, you have three different possibilities. In this case, none of the normals are collinear. Same with this picture here. Same with this picture right here. These are the last three possibilities for the intersection of three planes. These are the more interesting cases because these are when none of the normals are collinear. And that's true for all three of these examples. No collinear or no collinear normals, which basically corresponds to none of the planes being parallel. So that's true for all three of them. Is there anything else, though, that we can say about these planes? Well, let's maybe start with the intersection. Look at this first picture right here. Although there's these three lines of intersection, that just means that any two of the planes will intersect. All three of them, they do not intersect in the same spot. So actually, technically, we would say there is no intersection here. Unlike this example, where if you look, all three planes actually do intersect in this line right here. So there is, in fact, a line of intersection in this case. And finally, our last example, we finally have a unique solution or a point of intersection. All three of these planes do intersect at a single point. Now notice that these planes are all perpendicular, but that doesn't have to be the case. If I were to take, say, this plane right here and sort of like shift it or slant it to the right, they would still intersect at a point. In fact, these three planes look like they could be the x, y, x, z, and y, z coordinate planes, and that's a possibility too. So that's one thing that these all have in common, is that none of the normals are collinear. Is there anything else we can say about the normals? Just think about that for a second. In this example here, we often refer to these planes as forming a triangular prism. If you imagine the shape inside here, it's a triangular prism, like a tent. You could sleep in there if you wanted to. Think about the normals for those three planes. So that perpendicular vectors. It's actually best to think of the normals as being inside the tent that you might sleep in. What would they look like? Well, let me just imagine taking this triangular prism shape, and we're just going to rotate it so the entrance to the tent is facing us. And then we get a picture like this right here. Of course, that's only in 2 dimensions. Well, where are the normals to the 3 planes? Well, one of them is right here, one of them is right here, and one of them is right here. Do they have anything in common? They actually do. They're coplanar. You can draw them in the same plane, in this case, the white surface that I'm writing on right now. No matter what those planes look like, even if I were to take this plane and say shift it over here, rotate it over here, I still have a triangular prism, my normals are still going to be on the same plane, which is kind of like the same plane that the entrance to the tent is on, if that helps. So that's a property that's true. The normals are coplanar. Can be drawn in the same plane. Let's take a look at the line. Imagine drawing the normals for the line. Actually, I could do the same kind of thing. I always think of this as like a water wheel. I could rotate this water wheel so that it's facing me, and I would get a picture that looks like this. I can draw the normals for these planes now, and notice that they are also all on the same plane. And so this example, the normals are also coplanar. I know it's been a while in this course since we've talked about the idea of vectors being coplanar or being drawn in the same plane, but that's what's happening here. And then look at my third example. Imagine drawing my normals. I might draw one normal right here, the next normal right here, but notice that third normal is now going to have to come out of the screen or into the screen. And so in this case, the normals are non-coplanar. These 3 examples have a couple things in common. They have no collinear normals, and either the normals are coplanar or they're not. If I were to back up to the other examples, notice that as soon as 2 normals are collinear, then there's no point in talking about whether the normals are coplanar or not, because there's really only 2 normals, and 2 normals are always going to be coplanar. You can always draw 2 vectors in the same plane. And then in these examples, I mean, these are just silly. All 3 of the normals are collinear, so they're definitely coplanar. How do I tell if normals are coplanar, or if vectors, I should say, are coplanar? Do you remember that? We looked at something a long time ago called the triple scalar product. And we said if the triple scalar product of 3 vectors was 0, then those vectors would have to be coplanar. So in these 2 examples, it must be that n1 crossed with n2 and dotted with n3 must be equal to 0. Sorry if that's a little messy there. But that's the triple scalar product. So that's true for these 2 examples, but it's not true here. So in this case, n1 crossed with n2 dotted with n3 would not be equal to 0. Sometimes we put the brackets here, but we don't need to. Now, why is that the case? Well, it's a little bit hard to explain just by talking, but if you remember, we did discuss this. If normals are coplanar, if you cross 2 of them, you get a vector perpendicular to n1 and n2 and any vector in the same plane. So if they're coplanar, once you take the cross product, you dot it with n3, you must get 0 since n3 is also perpendicular to any vector perpendicular to both n1 and n2. And in this case, if the vectors are non-coplanar, so when you do the cross product, you get a vector perpendicular to both n1 and n2, okay, and also any vector in the same plane as n1 and n2. So this, what I've highlighted here, the cross product's a vector perpendicular to n1 and n2. If it's also perpendicular to n3, then the dot product would be 0, and if it's not, then the dot product's not 0. You might want to review that lesson. It was actually our second vectors unit, lesson 5, where we talked about the triple scalar product if you need to. So when we look at the equation of 3 planes, or just a linear system with 3 equations and 3 unknowns, we can actually figure out what kind of solutions we can expect before we even solve. This might be like when we were doing the equation, doing the intersection of 2 lines. We might decide whether there was going to be an intersection or not before actually trying to find the intersection. It's the same thing. So without doing any of the algebra, let's just see what we can determine about these 3 planes. I mean, the first thing I might notice is the normals. The first normal is 2, 1, 1. Remember, I'm getting that just from the coefficients, okay, on the variables x, y, and z. The second normal is 3, notice there is no x term, so the second normal is 0, 3, negative 2. The third normal is 3, 1, 2. Clearly, none of these normals are collinear. They're not the same. One isn't a scalar multiple of the other. So then I know that I've got one of the interesting cases. So I have one of these 3 cases here. Which one is it? Well, the only other thing I can look at is, are they coplanar? I need to use the triple scalar product. So it doesn't matter which 2 you cross first. It won't make a difference. I want to know if this is equal to 0 or not. If you do the cross product, you will get negative 5, 4, 6. Dot that with 3, 1, 2. And you'll find you get negative 15 plus 4 plus 12, which is 1. And more importantly, that is not 0. So I have 3 planes with normals that are non-coplanar. That means the intersection is a point. There is a single intersection point for these 3 planes, which means that there is a unique solution for x, y, and z. Forget about what that solution is right now. We'll look at that later. But for now, I know there is a single value of x, y, and z that will satisfy all 3 equations. Let's look at another example. X plus, okay, so we have these 3 equations here. We could start again by looking at the normals. The first normal being 1, negative 2, 3. The second normal being 1, 1, negative 1. The third normal being 2, negative 4, and 6. So I noticed something interesting here just by inspection. Notice that the first and third normals are in fact collinear. N3 is really just double N1. So I have two normals that are collinear. Notice that N2 is not collinear. So what case do I have here? If I just flip back through my notes here, I must have one of these 2 cases where 2 normals are collinear. Now, which is it? Well, I need to answer myself this question here. Are 2 of the planes the same? Or are they different? So the 2 planes, 1 and 3, are they different planes? Let's take a look at their equations. Notice that they are not the same plane. How can I tell? Well, if they're the same plane, they should have the same equation, and they don't. Compare the 9 and the 5. If all the coefficients in equation 3 are doubled from equation 1, and it's the same plane, then I would expect to see a 10 here. Since I don't have a 10, the planes are not the same. So I have no intersection. And I have that funny looking picture where we have 2 planes that are parallel and the third plane that's not, and it goes something like this right there. There's a terrible picture, but you've got the picture up above to look at as well. But that's the case we have there. Let's get one more example. Take a quick look. None of those normals are collinear. So then the next question is, are they coplanar? Well, if they're coplanar, we look at the triple scalar product again. 1, -1, 4, crossed with 3, 1, 1. That's the second normal, dotted with the third normal, 5, -1, 9. If you do this, you will find you get 0. I'm leaving that as an exercise for you to do. Which means we have normals that are non-collinear but are coplanar. So what do we have? Let's just take a look at that table again. We have one of these two cases. If the normals were not coplanar, we know it's a point. So we either have a triangular prism with no intersection or we have a line. And as it turns out, we're not actually able to determine which it is just by looking. So we either have a triangular prism with no intersection, or we have a line. It's actually not possible to tell. Really, all we can do is try to solve it and see what we get. And we will do that in a minute. The only thing we do know for sure is that we don't have a unique solution. Sometimes that's all mathematicians care about, whether there is or is not a unique solution. In this case, there is no unique solution. There might be an infinite number of solutions that form a line, or there might be no solutions as the planes form a triangular prism. Now, that's quite a bit to digest already. So I'm going to suggest that you might take a break and look at question 1 on the assigned problems. That's on our course webpage, or it's actually posted even in the comments of the YouTube video here. Take a look at that question, see how you do on it, check your answers, and then when you feel you're ready, come back and we will continue. Now let's look at the algebra. Let's look at actually finding the intersection of three planes, or we could algebraically just think about it as the solution to a system of equations. And I've written down the first example again. So we already found out that the intersection here was going to be a point. Sometimes mathematicians call this system consistent because it has a single unique solution. The first thing I'd like to point out is quite simple, that sometimes the constant is on the left side of the equal sign, sometimes it's on the right. It almost always makes more sense to rewrite the system like this. Take those constant values and put them on the right. Also think about the fact that we might line up our x, y, and z's as well. And there we go. So a simple change to that system. Okay, well, we're just getting started here. Things are getting real here now. We actually need to introduce what's called a matrix. And that sounds like a really confusing word in math, but it's actually pretty simple. A matrix is just an array of numbers. And I've written a bunch of examples down here for you. These matrices are not particularly big. Matrices can be as big or small as you want. They do have what's called a dimension. This first matrix we would call a 3 by 3. That's probably not surprising. The next one is a 2 by 3. It is a 2 by 3, not a 3 by 2. We always talk about the height of the matrix or the number of rows before we talk about the number of columns. Here's a 1 by 3, a 3 by 1, 2 by 2, another 3 by 3, and another 2 by 3. Now, why do we have matrices? What are they used for? Well, they're used for all sorts of things in mathematics. One thing they might be used for is to store a vector. In fact, these two matrices here might actually just be vectors. This is called a row vector, and the second one's called a column vector. In fact, if you take linear algebra in university, you may find that matrices are always used for vectors. The square brackets are very important. They are square brackets. They are not parentheses, and they're not straight lines. That actually means something else when you're dealing with matrices, so it's important that they are, in fact, square brackets. There's all sorts of things you can do with matrices. You can add them. You can multiply them using what's called matrix multiplication. It's actually very similar to the dot product. What we're going to use them for is one of their most common uses, and that's for solving systems of equations. Let me explain. A system of equations can be represented by what's called an augmented matrix. There's a lot of definitions in the next little part of this video. Some of them aren't super important for you to know, but I want you to be familiar with them. We begin by writing the augmented matrix for the system above. It would be a 3 by 4 matrix. So what we do is we take this stuff here, and ignoring the x, y's, and the z's, we write everything else in the matrix. 2, 1, 1, -4. That's the first equation. The second equation, notice there's no x's in the second equation, so 0, 3, -2, +2. Okay. And our last equation, 3, 1, 2, -7. Now, that's a 3 by 4 matrix, and it represents those equations. Now, what we usually do is, because there's an equal sign in the equations, we just do this little dashed line here. Okay, just to separate those numbers from the numbers on the right side of the equal sign. So what we're actually using the matrix for here is we're using it to essentially store the equations. I don't need to look at the original problem anymore. This is now my new problem, this matrix. So it represents a linear system of equations. And the goal, remember, is we actually want to solve this. We want to find x, y, and z. Should we use elimination? Should we use substitution? Should we use both? Well, we tend to use elimination. And what we can do is, because this represents a system of equations, we can do what are called elementary row operations. We can swap two rows. Okay, think about that. That doesn't change anything. If I swap row 1 with row 2, it's just like writing the equations in different order. I can multiply or divide a row by a non-zero constant. Well, that makes sense too. You can take any equation you want and multiply both sides of the equation by, say, 2. So that means that I can do the same thing to any row in this matrix. I can double it or triple it or divide it by 2 or multiply it by -10, whatever I want, and I still have a matrix that represents the same system of equations. And then finally, the last one, I can replace a row with the sum or the difference of itself and a multiple of another row. Think back to elimination. That's really all you're doing there. You can add and subtract equations. We know that, and that's the process of elimination. So I can do the same thing with the matrix. I can take, for example, row 3. I could add it to row 1 and then replace row 3 with row 1 plus row 3. Probably wouldn't want to do that, but I could. I could take row 3 and add it to row 2 and then replace one of row 2 or row 3 with that result. In that case, that might make sense, because notice I'd be eliminating the z's. So elementary row operations are really similar to those using the elimination method. All the matrix is doing is it's organizing our work. If you tried to solve this system using elimination, it can be done. But you would find yourself going around in circles, eliminating a variable only to reintroduce it again somewhere else. And you find the work gets very confusing. You were able to do that, hopefully, use elimination. You're hopefully able to do that using 2 equations and 3 unknowns for when we did the intersection of 2 planes. But when you do the elimination method with 3 planes, it can get very, very confusing. And so this is going to help you. So our goal will be to make entries in our matrix equal to 0, which corresponds to using the elimination method to eliminate variables. In fact, one way of looking at it is, if we go back to our examples of matrices, notice these 2 matrices right here at the end. Those are actually called identity matrices. You don't need to worry too much about that definition. Notice that a lot of the entries are 0 with 1s on the diagonal. It's kind of a good strategy to try to do that with our matrix. So I'll work through the example, the first example. We know that this intersection is going to be a point. And for now, follow the process of what I do. And at the end, I'll give you a strategy for why I chose to do things the way that I did. So if I look at this first example, I'm quite happy to notice the 0 there. That actually makes this example a little shorter than some other examples. In fact, if that entry wasn't 0, I'd actually make it 0. The next thing I'm going to do is I'm going to make this entry here equal to 0 by performing some row operations. So how do I do that? Well, I'm going to combine it with the first row or the first equation. And what I'm going to do is I'm going to take 3 times row 1 and I'm going to subtract 2 times row 3. So notice that will give me a 6 here minus 6 to give me a 0. As I do that, I'm going to replace row 3 with the result of 3 times row 1 minus 2 times row 3. So the other 2 rows are going to stay exactly the same. Okay, so I get 0, 1, since 3 subtract 2 is 1, negative 1, 2. Now, as I did this, notice this is my notation here above the arrow to show the row operation I'm doing. I always stick to this notation where the second entry, the row 3 here, is the row I'm going to replace. You don't have to do it that way. It just makes things a little bit easier to follow. Okay, and then I just went ahead and did that. So like, for example, I got 3, subtract 4, gave me the negative 1, negative 12, subtract 2 times negative 7 will give me 2. So this matrix represents the same or an equivalent system of equations as the first matrix. It's just a little bit simpler because it has more zeros in it. The next thing I'm going to do is I'm going to look at this 1 right here, and I'm going to eliminate it. By combining it, I could either use row 1 or row 2, but I actually want to use row 2. Can you see why? If I were to go row 1 minus row 3, that would eliminate the 1, but the problem is I would wreck the 0 because I would get a 2 there instead of 0. So if I actually use row 2, then I add an extra 0 without, wrecking that 0. So to do that, I would then go row 2, subtract 3 times row 3. So row 3 is the one that's going to change. The other rows will stay exactly the same. And when I do that, I get 0, 0, 1, negative 4. And now I'm going to stop because I actually have something quite useful. Look at equation 3. It's been simplified so much now that it's actually z equals negative 4, right? Because that's 0x plus 0y plus 1z equals negative 4, or z equals negative 4. So we've actually solved for one of the variables. And what we can do is we can do what's called back substitution, and now we can solve for x, y, and z as well. So let's do that, and then we'll talk about some of these other definitions here as well. So if I look at equation 2 now, or row 2 of the matrix, it tells me that 3y minus 2z equals 2. Well, if z equals negative 4, then I can substitute that in, and I get 3y minus 2 times negative 4 equals 2, or 3y plus 8 equals 2, 3y equals negative 6, and so I've now solved for y as well. Y is equal to negative 2. And finally, the first row of the matrix, the only equation that didn't change, 2x plus y plus z equals negative 4. And now I can substitute my values of y and z into that equation. So I get 2x plus negative 2 plus negative 4 equals negative 4, or 2x minus 6 equals negative 4, gives you x equals 1. And so there's my solution, my point of intersection, 1, negative 2, what was it, negative 4. What we just did is called Gaussian elimination. And we ended up with a matrix in what's called row echelon form. I'm not going to worry too much about these definitions, but row echelon form essentially is everything. If you look at this matrix here, my row echelon matrix, everything below the diagonal, see the diagonal 2, 3, 1, everything below the diagonal is equal to 0. That's a matrix in row echelon form when that happens. And in some cases, you'll actually get a row of entirely zeros, and that needs to be at the bottom. This was a somewhat simple example because I started with the 0 here. That just saved me one step as well. So although we solved that system of equations and found that point of intersection, I want to show you something a little different. So I've rewritten the same matrix we finished with from that example. There's nothing wrong with where we stopped. You can see that z equals -4, and you can go from there and solve for x and y. But another approach would be to continue doing row operations and to continue making entries equal to 0. We've already made the entries below the diagonal 0. Now let's make the entries above the diagonal equal to 0 as well. And then we'll talk about these little definitions up here. So I'm going to start with the 1. In order to eliminate the 1, I can take row 2 and subtract 3 times row 1. And I will get -6, 0, -5, and 14. And then 0, 3, -2, 2. Sorry, that should have been a -2 right there. 0, 0, 1, -4. Okay, the next one that I will attempt to make 0, or I will make 0, is the -5 in the top right. And to do that, I'm going to do 5 times row 3 plus row 1. That will give me -6, 0, 0, 6, 0, 3, -2, 2, and 0, 0, 1, -4. Notice that I used row 3 to eliminate this and not row 2, because if I'd used row 2, I would have wrecked the 0 I just made. And then finally, I'm going to make the -2 equal to 0, and I will do that also using row 3, 2 times row 3 plus row 2, and that'll give me -6, 0, 0, 6, and I get 0, 3, 0, -6, 0, 0, 1, -4. And finally, there's one last thing I'm going to do here. I'm going to now make the diagonal numbers I have here, -6, 3, 1. Sorry, that's a little bit messy there. I'm going to make them all into 1s. So this is already a 1, but I'm going to change row 1 and row 2. So I'm going to do -1/6 times row 1. And that's going to give me 1, 0, 0, 1. And I'm also going to do 1/3 of row 2. And that will give me 0, 1, 0, -2, 0, 0, 1, -4. Do you notice what I've got now? Rather than needing to back substitute, I can actually just look. Each equation just gives me an answer. The first equation says x equals 1. The second equation says y equals -2. And the third equation says z equals -4. So this is an option. Instead of back substituting to find x and y once you solve for z, you could just keep reducing and you could actually get x, y, and z, like basically reading the numbers out of the matrix. I mean, you've almost got it in this last step here, and then one more step gives you the answer. That's called Gauss-Jordan elimination, okay? And rather than being in row echelon form, it's now in reduced row echelon form. Now, I'm not going to be real picky about you knowing those definitions, but I think it helps to at least hear about them. Essentially, with reduced row echelon form, we try to make this part of the matrix into an identity matrix. That's 1s along the diagonal and everything else 0. Now, you won't always be able to make that exact pattern there. Sometimes you might end up with a row of 0s at the bottom, or even 2 rows of 0s at the bottom. Now, I did this example. I don't really care, by the way, whether you use Gauss-Jordan elimination or Gaussian elimination. It doesn't matter to me. You might find Gauss-Jordan elimination is easier in some examples, and I'll show you one like that later as well. But how did I decide what order to eliminate entries? There is a specific order that makes things a lot easier, and here it is right here. Okay, these, what I've noticed here, I'm just showing the coefficient matrix. I've left the constant part of the matrix off. But these are the order that I would recommend that you eliminate entries. Start with number 1, and then number 2, and number 3. Once you've done number 1 to 3, you're in row echelon form, so that you could use back substitution after that if you want to. You could stop basically after number 3. That's what I'm trying to say. Or you could do Gauss-Jordan elimination and then continue by doing 4, 5, and number 6 as well. So in most examples, it's going to be up to you to decide whether to do that. I will give you an example where I do think Gauss-Jordan elimination makes the question a lot easier rather than trying to back substitute. It just gets too complicated. Here's a very similar example. So how about you pause the video, then you solve this example using a matrix as well, keeping in mind that I've now given you the hint, and that's the order that I choose to eliminate things in. If you want, you can just do 1, 2, 3, 3 row operations and stop and solve the system, or you can do all 6. It's totally up to you. But I'm highly recommending that you pause the video or stop the video and try this yourself. I'm going to do the same thing, and we'll see what the solution looks like. Okay, and there it is. Here's my solution. Now your solution doesn't need to be exactly the same as this. My guess is the first few row operations will be. I've highlighted the entry I'm trying to eliminate each time. I start with the 2, and then move on to the -3, and then the other -3 to eliminate those 3. So once I get to this matrix right here, I could have stopped. You can see right here that -11z equals -44, z equals 4, sub that into the second equation, solve for y, sub both of those into the first equation, and stop. So you might have finished here, and that is absolutely fine. The answer is this one does work out to a point. Okay. You also could have told that it worked out to an intersection as a point by looking at the triple scalar product of the normals. That's not necessary to do because you can tell when you go to solve it that that's what happens. So you could definitely stop here, but just to show you what would happen if you kept going, I did keep going. Okay, now this gets a little bit confusing. Some of the numbers get a little bit big, but again, I keep eliminating variables. Notice the only step here, I did not eliminate any variables. I just got tired of all the negative signs, so I multiplied each row by -1. Okay, continue to eliminate entries. Sometimes as I went along, I saw a -11 and a -22, and I thought, well, let's just change that to a 1 and a 2. And 11 and 44, let's divide both of those by 11 as well until I finally get my answer here. So no matter how you did it, you should get x equals 2, y equals 1, z equals 4. It is easy to make a mistake when you're doing this. There's no doubt. As I did this example, I made a mistake, and I had to figure out where my mistake was. Sometimes if you can't figure out where you're wrong, you're better just to start over again. Be careful, keep your work neat, show your row operations, and all that will help you to minimize your errors. So that was a very similar example as the one we did. Let's take a look at something that's a little different now. So this is actually one of the examples that we looked at very early on in the lesson and determined that there was no intersection for these 3 planes because the first plane and the third plane were parallel planes but distinct. And so we get a picture something like that right there. But let's say that we were to go to solve this anyways, and let's see what happens when there's no intersection. We start by putting this into an augmented matrix, just like this. Okay, and performing our row operations, we look to get rid of the 1 first. Row 1 minus row 2 will do that. So 0, -3, 4, 5. Then I go to eliminate the 2 in the bottom left. I do that doing 2 times row 1 minus row 3. And that's where things get a little bit interesting. We get 0, of course. But then we go -2 times 2 is -4, subtract -4 gives us a 0. and then we actually get another 0. And then finally, for our last value, we get 18. Subtract 5, we get 13. I think of this as being a 0 row, okay, even though the last number isn't 0. It kind of signifies that we should maybe stop and take a look at what we got. The last equation now says that 0z or 0y or just 0 equals 13, which is, of course, not true. So we've got a contradiction there. So there is no solution. There is no way that all three of these equations can be true at the same time. So when we use a matrix to solve a system, if the system has no solution, it's very easy to see that pretty quickly. Try our next example. That brings us to our third example, where we couldn't tell what type of intersection exists. None of the planes were parallel, since none of the normals were collinear. The normals were, however, coplanar, which means that we either had a triangular prism with no intersection, or we had an intersection that was a line. So the only way to solve this is to actually try to solve it and see what happens. We can put it into an augmented matrix, perform row operations, and see what our result ends up looking like. So our first goal is to eliminate these three entries right here. So why don't you go ahead and do that, and I'll do it as well, and you can check your answer in a minute. So there are the three row operations, eliminating each of those numbers in order. Now notice when I try to eliminate this last -4, I again get 0, 0, 0, -7. Well, what does that mean? Well, that looks a lot like the previous example. 0 cannot equal -7 according to the last equation. There is no solution. So it must be that we actually have the triangular prism up here and not a line of intersection, because that last equation can't be true. So there can't be any values of x, y, and z that satisfy all three equations. But this is the only way to figure that out. One more very important example to come up. So let's take a look at this last but pretty important example. I've got the system here. I've immediately put it into the augmented matrix. Be careful with the last equation. There's no z value, so we put a 0 in for z there. I've decided not to look at the normals here. Clearly, they're not collinear, but maybe they're coplanar, maybe they're not. If the intersection is a point, the algebra should show that. So let's just go ahead right into the algebra and start eliminating in the correct order. You've noticed that if you haven't followed my order of eliminating, you're going to find you end up just going around in circles a bit. It's not wrong, it's just not efficient. Okay, so excuse me, 3 row 1 minus row 2 will give me 0, 4, -8, and -12. I'll leave the other two rows the same. Now, as I choose, I'm now going to eliminate the 1. I can do that simply by taking row 1 and subtracting row 3. At the same time, though, I notice the second row, everything's divisible by 4. I don't know about you, but I prefer to deal with smaller numbers. So I'm going to do 1/4 of row 2 at the same time, just to make that row a little bit simpler. So that gives me a second row, 0, 1, -2, -3. And then my last row, I get 0, -1, +2, and -2 surprise me 3. Okay, I go to eliminate this guy right here by adding row 2 and row 3, and that's usually where the interesting step is. Because what happens is I get everything eliminating, so I get 0, 0, but I also get 0 from my last entry. Well, that is not no solution. It's not like we have 0 equals 5 or 0 equals 10 or something like that. We have 0 equals 0, which is always true. So this last equation isn't a contradiction. There is definitely a solution here. Now, I can tell that there's going to be an infinite number of solutions to this system. if the planes aren't parallel, after you do a few of these, you'll start to see the pattern and realize like this is a line. There's a line of intersection here. The normals are coplanar as well. If you check that triple scalar product, you'd find you get 0, so they are coplanar. So the intersection is a line. Now, how do we find the equation of that line? It is possible to stop here and use back substitution to find the equation of the line. You could basically let z be your parameter, sub it in here, and solve for x and y in terms of z. But I think there's something that's a little bit easier. What we can do now is we can still continue to eliminate. So this is where I would recommend you try the Gauss-Jordan elimination. So we try to eliminate more entries to make things a little bit easier. And this one's pretty easy to eliminate because we just do row 2 minus row 1. And we'll get negative 1 because we did 0 subtract 1. 0. Negative 2 minus 2 is negative 4. And negative 3 subtract negative 2 would be negative 1. Just like that. Now, I could continue to start eliminating, and I would move on to the negative 4 next. And I try to eliminate it, but look what happens when I do that. Normally, I would use row 3 to help me out to eliminate the negative 4, but I can't do that in this case because it's 0 there. So I have to use row 2, but if I use row 2, I'm able to eliminate the negative 4, but I'm going to wreck one of my zeros, so to speak. So if you'd like to see what that looks like, I can show you. We would do something like, let's see, 2 times row 2 minus row 1. And I would get 1, 2, 0, and 0. And you can see the problem here. Negative 6, I get negative 5. Like I'm going to go around and kind of go around in circles now. Because although I was able to eliminate the negative 4, I wrecked the 0 that I made here. So actually, that's a sign that we probably should stop here. I'm going to erase this. I don't want that. I have something very useful, especially because I know the intersection is a line. Sometimes I look at the last equation as being like 0z equals 0. It could also be 0y equals 0 or 0x equals 0. It doesn't matter. So we say like there's no restrictions on z, basically. You might say something like let z equal t. In which case, if I look at equation 2 tells me that y subtract 2z equals negative 3. Or y minus 2t equals negative 3. And I get y equals negative 3 plus 2t. I look at the first equation, which is negative x minus 4z equals negative 1. But of course, z is equal to t, so negative x minus 4t equals negative 1. And I can solve for x in terms of t. Now notice if the y entry wasn't 0, I would just have to sub in negative 3 plus 2t in for y as well. And I could still solve for x in terms of t. That would be what you do if you decided to stop with this matrix here. You'd have to do that. You'd have a y value in here as well. So eliminating that one extra value does save you quite a bit of work. Okay, negative x equals minus 1 plus 4t, or x is equal to 1 minus 4t. And there's my solution. My intersection is a line. That line has the equation x equals 1 minus 4t, y equals negative 3 plus 2t, and z is equal to t. The line of intersection. Okay, that's it. Thanks for making it through this rather long lesson. There are some questions for you to try with this. The link to that is below, or it's on our course webpage. I highly recommend you go through those problems. I haven't shown you every single possible case that you could have. Some of them are pretty simple. Sometimes there's other things that come up in examples that make things a little more difficult. Maybe your intersection is a line, but the line has z equal to 5. I mean, that's part of the equation of the line, and z can't be your parameter. That will happen as well. Maybe you uh, there's other possibilities you haven't seen yet. I can't go through every single example. What I need you to do is I need you to practice this and to take a look at the solutions if you get stuck and understand how we can solve these problems. If your intersection is a line, it is possible that you have a different solution than someone else. It doesn't mean it's incorrect. One way you could check a solution, I could pick a value of t here, say t equals 5, and then I'd have my x, y, and z values if t equals 5, and then I could go and I could take those x, y, and z values and make sure that they are in fact solutions to each of these three equations. That's one way to check an answer. Although there are an infinite number of solutions to this system, that doesn't mean that every single x, y, and z value will be a solution to the system, only the ones that lie along the line that we found. It's a really important part of linear algebra. This is the starting point for where linear algebra in university would go. There's a lot of matrix operations in a university algebra class, a lot of solving systems using matrices as well. So take your time and reach out if you have any problems. Okay, bye for now.